Hello everyone, my name is Alexander Dugan. I'm a Senior Application Engineer for ESTECO. ESTECO is a company that is an independent company that specializes in numerical optimization technologies. I'll just walk you through two of our products. modeFRONTIER is our desktop client. This is a tool where the subject matter experts can build their piece of the MDO, the multidisciplinary optimization process. And then we have VOLTA, which is our web-based platform for collaborative MDO. It also has an SPDM, so simulation process data management component to it, so that we can facilitate the subject matter experts sharing and collaborating with the system level experts, so that we can more easily break down the silos that may exist, that prevent you culturally sometimes from tying together multiple disciplines together to do an optimization. We're going to walk through two case studies. The first one is based off of a NASA paper which was published in the late 90s with optimizing a supersonic business jet. So the whole goal here is MDO. There's also other terminology, MDAO, MADO, but basically it's multidisciplinary design optimization. So the goal here is to add as many disciplines as possible of your system, model them, and then stitch them together and optimize it as a system. So this example will give you a flavor of what that looks like within our tool sets. We'll actually touch on 4 disciplines as part of this example. Of course, you could have many, many more, and hopefully you'll get a sense of how that scales. In this case study, we'll model the structure, component, aerodynamics, propulsion, range of a hypothetical supersonic business jet aircraft, and we'll link them all together. And the end goal, after running the MDO, we want to maximize the range of the aircraft while also minimizing the aircraft's weight. So with that, let me jump to our desktop tool, modeFRONTIER. So this is a blank workflow. We'll start from scratch. And I'll walk through building 2 out of the 4 for time purposes. And then I'll just show you the completed other 2 disciplines. And then we'll stitch it together in the MDO. So the range component actually is a MATLAB code. So you can see on the left-hand side, modeFRONTIER has a suite or library of built-in integrations to commonly used tools, like you can see CAD packages here, Creo, which we'll touch on in the next example, and also other tools like MATLAB. Python is here as well. You have other commonly used tools like Microsoft Excel. These are built-in integrations, makes it very easy for us to link modeFRONTIER and VOLTA to third-party tools. And even if you don't see one of your tools, commonly used tools here, that's okay. We have other ways of building, let's say, custom integrations, in-house codes, or from programmatic command line, we can also automate the connection between the tools. But for this example, we're going to use MATLAB. The MATLAB integration requires you to point to a script file. We're going to call this a model file. This model file can reside locally, but ideally you'd upload this into the VOLTA framework. So we're coming in at the stage where we've already uploaded our model into VOLTA, and now I can browse to it. And with that model in VOLTA, as you'll see when we jump to the VOLTA framework, you get the added benefit of having version control and ownership. So the subject matter expert will maintain ownership over their models, and they can maintain their models over its lifetime. So let me pull in the range model file. And here you can see the versioning, so I'll just pick the latest version. The model is a script, but it has a snippet at the top which allows us to parameterize that script. So here you can see all of our input parameters within the model. These are, of course, range specific. I can drag these left to right. This establishes a connection from a modeFRONTIER variable to a model parameter. So this gives modeFRONTIER and VOLTA control over changing these parameters within the model. And the single output of this model is just going to give us the aircraft range. Apply this. So with this, the workflow is actually built. Very easy. It doesn't require a lot of manual work. And the next step would be defining the ranges. So lower bound, upper bound. So rather than type those in manually, I'm going to just paste them here within modeFRONTIER. So now my lower bounds, upper bounds are all set. Ideally, you want to exercise the model over these ranges to make sure it's valid. Next step would be defining a strategy on top of this. So within modeFRONTIER, you can do just a single run, so run through maybe just a baseline design. You could explore globally the design space with the design of experiments, or you could do an optimization. And then later on, I'll just mention we also have capabilities to do uncertainty quantification, so you can design for robustness or reliability as part of your optimization strategy. So these are kind of the 6 scenarios built into modeFRONTIER. I'm just going to do design of experiments because we'll show the optimization later once we get to the MDO phase. But it's always good to exercise your disciplines, the single disciplinary type workflows through either a design of experiments, just to make sure that it's working correctly. So here I can also set in, fine-tune my input domain, whether my variables are continuous, maybe they're discretized, so maybe they can only be of integer type, or maybe it's constant. If I want to take it out of the study, I can set it to a constant. Output domain, simple, just what you want modeFRONTIER VOLTA to record after running the model. In this case, we want to record the range value. And then lastly, you'd have to add in a DOE. And so modeFRONTIER has built in 15 or so different type of DOE algorithms. They range from classical ones, which are just sweeps, like a full factorial, all the way up to more advanced ones, like the uniform Latin hypercube, which is a Latin hypercube algorithm with a uniform distribution. And here I can tell modeFRONTIER to come up with 100 different combinations of all of my inputs. And I can have modeFRONTIER churn through this. However, this is not part of this case study. What really I want to do is save this now into the VOLTA framework. So if I'm acting as the range subject matter expert, at this point I would want to save this, so I can go save as. Rather than save it on my local machine, I want to save it into VOLTA. So here modeFRONTIER and VOLTA are tightly coupled. I can go here and save it up into VOLTA. I can give it a name. And I get to decide where I want to place it within the VOLTA file system. So I've already uploaded that model to VOLTA. I just want to show you another piece of it. So we'll go through the propulsion discipline, and this one, just to give you another flavor of what modeFRONTIER and VOLTA can do, this one won't be model based in that it won't be calling a third-party tool. It'll actually be response surface based. So response surface goes by many names these days, commonly referred to as surrogate models, meta models, machine learning, artificial intelligence. These kind of all are under the same umbrella. Basically, we start with a data set, and we want to train a mathematical representation using this data, so that I can use it in place of a third-party code, and it in itself becomes somewhat of a model. So we do have a RSM training toolbox within modeFRONTIER. It's wizard-based, so you can quickly walk through it. It does include validation, sensitivity analysis if you wanted to filter out any unimportant inputs. Maybe that inputs that don't have any effect on my output, I can remove those. And then within modeFRONTIER, we do offer quite a large library of response surface algorithms. So these range from classical methods like a polynomial fit all the way up to neural networks, or even we've now included artificial intelligence type machine learning algorithms as well for larger data sets. The nice thing is I can pick many of these different strategies and algorithms and have modeFRONTIER churn through them and tell me which one performed best at predicting my response. So I'll go ahead and kick this off. I can multi-thread if I have more cores just to speed up this. And as you'll notice, for each output, I've trained 5 different response surface models, and modeFRONTIER will automatically tell me which ones fit the best. And I can just quickly star these. As you can see, if r squared is my error metric of choice, I want to pick one that's closest to 1. So I'll just go ahead and pick these, highlighted in green. And now if we jump back into modeFRONTIER, we have a whole set of RSM models that I can now use to calculate my propulsion discipline. And again, these can also be uploaded up to VOLTA, so I can save this into VOLTA with, I can save this up into VOLTA, and it can be my propulsion model. So to close out the other disciplines, I'll show you the aerodynamics piece. This one is what we consider, what we call a MyNode. This is a custom built integration. So if you have an in-house aerodynamics code, hypothetically, if you have that, we could build a MyNode wrapper around that, and then it becomes like any other integration. You could pull it in, select your model, build this workflow very, very easily with little upfront cost. So that's 3 out of the 4 disciplines, and the last one is the structural component. So this is calculating stresses on the aircraft. It is just a code, in this case a JavaScript code, but you could imagine if I want to ramp up fidelity, it's multi-fidelity model, I could pull in maybe an FEA code here to calculate stresses for me rather than predicting it using the equations. So now I've saved all of my models, all of my processes within VOLTA, and I can show you what that looks like. So if I jump to the VOLTA platform now, the VOLTA platform is installed, deployed on premises. So we work with your IT, make sure we're meeting all of your IT requirements. We work with them to deploy it, and then work with them to maintain it, upgrade it as needed. It is already deployed on the Lockheed network, actually within your GovCloud, AWS GovCloud. So you do have access to it. It is user account based, so you do need to get a user account to actually log into the VOLTA framework. But once you're here, you're first presented with the kind of the SPDM aspect of VOLTA. So if I jump to this Supersonic business jet example, you can see we built, or you can see the 4 disciplines here, and the one that we built, for example, range, if I browse in here, you can see the actual MATLAB file, the script, I can see it here. I can version it if I am the owner, so I can create a new version if it changes over time. Maybe I want to make some modifications. I can just simply create a version, drag and drop in the new model file, and VOLTA will keep track of that. Along with all of the somewhat generic model files that you put into VOLTA, the process is also stored here. So that range workflow that we built that has MATLAB integration included, I can quickly click on this and I can see the model itself with the input parameters going into MATLAB and it calculating the range. Along with that, we treat it, of course, special because it is a process automation workflow. We can actually exercise this, becomes somewhat of an actionable model. So if I go to plans, I can see that I have that plan already created, the one that we built within modeFRONTIER, the DOE. I can create a new plan if I wanted to. Let's say an optimization plan. I'll call it optimization. And again, this is all on the web. So here I can define my input domain with all of my, let's say I want to make all of them, for example, variables, continuous. I can quickly do that. I can turn on and off if I didn't want anything. And then I can define my objectives. The next step is defining the optimization strategy. We are an optimization centered company. So we do have a research team. We have a numerical team that kind of develops our own type of optimizers. And so you can see the full list here. The gradient-based, evolutionary, the heuristic optimizers, these come mainly from public domain. Of course, we add our own flavor. The multi-strategy algorithms are built in-house and are proprietary to ESTECO. And I would mention that most of these are used by our customers. And I'll just pick one, the easiest one, which is PyLopt. It is fully autonomous algorithm, so it'll run and stop on its own without any user input. Getting to the run part of it, so you can tell VOLTA to run in two ways. You can tell VOLTA to run all in one mode, meaning the entire process automation is handled by a single machine. This is quite useful for simple, maybe one or two models within a workflow where one machine can take it. But as you can imagine, if you build more and more complex process automations involving tens of different codes, it's unlikely that a single machine would be able to handle it. One common scenario is we want to run distributed mode, meaning we run across machines, where maybe a Windows workstation takes care of the CAD, but then we have the solver, the FEA, the CFD, which we want to send off to an HPC. So in that case, it is distributed mode, where there are many machines required to run the execution. You can ramp up the number of concurrent executions depending on how much hardware you have connected to VOLTA. So the more compute hardware you assign to VOLTA, the more throughput you can get. Especially if you link an HPC to VOLTA, right? We can really ramp up this number of concurrent executions. And then lastly, where do you want this sent to? Like I mentioned, you can send it to a workstation somewhere, a group of workstations. You can send it to a cloud, or you can send it to a combination of these, maybe an HPC as well. Once the plan is completed, as you can see, I have all green check marks. It's ready to go. I can save it. Once it's saved, I can simply run it. So this will actually kick off the run. And VOLTA is keeping track of all of the executions that are taking place. All right, so let's look at the big picture now. We want to go from a single disciplinary type optimization like you just saw me run here, just the range aspect, into a multidisciplinary optimization. So to do that, we still leverage modeFRONTIER, but at this stage it becomes quite trivial to build an MDO workflow, which is kind of interesting, but it's very scalable. So you can imagine the structure workflow that I showed you, published and maintained by the structure subject matter expert, the aerodynamics workflow built and maintained by the aerodynamics subject matter expert, propulsion, and you see one is missing here, which is range. So I just want to show you how you would add in another discipline. We use the VOLTA icon here to call another workflow built by another user. So the sharing aspect is there, right? So that subject matter expert needed to share his model and his workflow with me for me to access it. And there's a number of ways to do that within VOLTA. But I can, at this point, call it. So if I just link this together, I can call this one range. And if I go in here, I'll select the range workflow that was shared with me. I can find it here. And I can tell it to always pick the latest version. Range has its own set of inputs and outputs, so I do need to run this parameter chooser just to make that link from the MDO level, system level optimization run into the model, the lower level single disciplinary workflows. You don't need to link all of the inputs, only the ones that need to change at a higher system level. But in this example, I will be selecting all of the inputs and the single output, which is range. So as I mentioned here, I'll just select all of the inputs, which all of them will be controlled by the MDO level. And you can see here it's already found upstream dependencies. And it's asking me, do you want to link to existing? And yes, I do. So upstream data is fed as input into this model, and then range is coming out as my single output. So hopefully you get a sense of how this is scalable as you add more and more disciplines into your MDO study. This again gets uploaded into VOLTA. However, there's a unique aspect to this, is each VOLTA icon here can run on different compute hardware. So if structures have a group of machines that run their structure code, you can tie those machines to VOLTA and tell VOLTA to run on those structure workstations. Likewise with aerodynamics and propulsion and range. Maybe aerodynamics is expensive, so I'd want to outsource this to a cloud environment, or maybe an HPC to get more throughput. Once this is saved within VOLTA, I can go in here and I can run it as well. You can see I already have a plan here, which is run pilopt. In the interest of time, I'll just skip to an already completed session. Every time you run a plan within the VOLTA framework, VOLTA is keeping track of all of the, we call sessions, all the data that's generated from running these studies. Here's one. This was run using our pilopt algorithm, and you can see it ran quite a few simulations here, over 1,000. So this is over 1,000 calls to each of the disciplines for me to generate this result set. Looking at the numbers here, literally right next to the results from the study, I have a dependency tree, so I can see which version of each and every model that was used to generate the results. So if I need to come back later, reproduce something, I can easily do that because I have the full traceability of the dependencies here. Rather than looking at just numbers, we want to actually make some insights into the data. And so we do offer what we call the VOLTA Advisor, and you can add in a number of different charts, visualization tools for you to make sense out of the data. Inevitably, when you do run multi-objective type studies, like in this case, we're trying to maximize aircraft range while also minimizing its weight. You end up with a Pareto front or trade-off space. And this is the point where you want to be at. So now multiple stakeholders can come in. They can weigh their different KPIs and come up to maybe a compromised design solution. Ideally, you would never pick a non-Pareto design, so a non-optimal design. So you can quickly filter those out. I can say, just show me the best designs. And then maybe add in a parallel coordinate chart where I can have the stakeholders come in, all looking at the exact same data, right? Because it's on the web, they all have access to it. There's no copying of data, right? So everyone's looking at the most up-to-date data. I can set different filters on this. So maybe weight is very important to me, while maximizing the range is less so. So I can just set a filter here. So I end up with some compromised solution right in the middle of the front. You can even click on these points to get more refined information about what that design configuration looked like. Along with those two charts, we do offer a number of other ones. As you can see here, you can do correlation studies. For example, if you wanted to kind of determine what inputs have most effect on my output, you can kind of do that. If I pick, for example, my range output, I can see lift has a fairly substantial correlation, whereas, let's say, engine scale factor, right, isn't really causing that much correlation among my to my outputs. So with that, I'll switch to our second case study, which is a simple beam optimization problem. This will include 3 objectives. Mainly, I want to show you the Creo integration and also how to integrate with any third-party code. In this case, the costing code will be integrated with what we call the Easy Driver. We don't have a built-in direct integration to this tool. And then the third domain is FEA. This will be done using Abaqus as the solver. So let me quickly show you what the Creo integration looks like. Before you can start, you need a parameterized Creo part or assembly. And by that I mean it's actually set up to parameters that are linked to dimensions within the part or assembly. So if you make a change here manually, you will need to be able to see the update once it regens. So if I increase the height. Once you've done that aspect, now we can easily tie this into modeFRONTIER. So this beam part is also uploaded into VOLTA. I can drag and drop in the Creo integration. I can pull in the Creo part, again, from VOLTA. And again, parameter chooser. So now I can detect those same parameters that you just saw in Creo. They are exposed here, but they're not single values anymore. I'm going to extend them right into a lower bound and upper bound. So if I drag these left to right, and as part of my output, maybe I want it to calculate volume and mass. Maybe more meaningful is to actually export the modified geometry file. So this can be native or generic format. So if I go into CAD export, I can have it store the native Creo part every time it makes a change, or I can tell it to export as an STL. And within each one of these exports, we do have a set, all the settings right to define how you want this exported. So for example, STL, I can ramp up the quality as needed. With that, I have a built workflow now, integrates with Creo. Very simple and easy to do. However, a little bit more upfront cost if I switch to the next discipline, which is the costing calculator here. This is going to run a tool called a priori. We don't have direct integration, but we can run it from command line. It does support batch execution. And so for us to automate that type of execution, we use the Easy Driver. So this is, again, proprietary to ESTECO. It makes it fairly easy to integrate this code. So for example, I can come in here, plug in a custom script, whatever I need to do to run this third-party code. And then once it's done running, I may have some downstream processes used to extract the output that I want. So once I have all of the disciplines, as you saw with the business jet example, I can stitch them together and do the MDO. I'm not going to show you the FEA component, it's already there. If I jump back into VOLTA, I can show you what the finished result looks like. Go into the beam example, and we can take a look at the Creo Abaqus a priori, all the runs that have been done. Again, if I go into the sessions, I can see all the different optimizations I've ran on this. We can take a look quickly at the results. In the dashboard environment, I pull up the scatter bubble. In this case, you're seeing on the y-axis here is the log of displacement. That's why you're seeing it go a little bit negative, but it just looks better. And then cost. So I want to minimize the cost of this beam while also minimizing the displacement. If I'm interested more on the cost side, I'll pick more toward the left. So maybe design 154 is the one I'm interested in. I actually had it export an image for every run. So if I want, I can zero in on design 154. Just a sec. 154 isn't feasible. Let me apply the filter here so I only show you the best designs. Again, if cost is more important, maybe I'll pick this one instead, 152. Let me go here. We can look at design 152. And you get a stress profile like this. It looks like a standard I-beam. Also, what's kind of neat is if you export as an STL, you can actually render this directly on the web. Just to show you an example of that, I can go to a different set of results and click on this STL, and now you can see the beam, and I can actually rotate it and see what it looks like. So those are the two case studies I'd like to emphasize. However, we're working on a number of different aspects as part of our collaboration with Lockheed. We are working on a PLM coupling to Windchill and Teamcenter. So maybe the Creo part you want to pull directly from the Windchill environment. So we're working on building that bridge. VOLTA itself has a suite of RESTful APIs, so you can build even your own flavor front end on top of VOLTA. If you wanted some Lockheed customization done, you can use our APIs to do that. We just recently imported a BPMN editor inside of VOLTA to further help facilitate building these complex MDOs, breaking down the silos, so you can build a business process that you can reuse later to help you facilitate your MDO studies. And I did also mention the UQ aspect, so you can also do uncertainty quantification as part of your optimization. So with that, thank you very much.